Inslogic ABS-PC PC ABS. Unfortunately, this is in black color and this one is reinforced with glass fibers, but anyway, I hope that we will understand better the difference between these three materials. Hello, welcome to my tech farm. Inslogic, it's a brand owned by Sanlu and they're focusing more on professional product line, and they sent me some technical filaments for the testing. And these are ABS-GF10, ABS reinforced with glass fibers in natural color, PC or polycarbonate also in natural color, and PC ABS blend in black color. I got two spools from each. Only for PC ABS I got one smaller too, and I'm curious how it looks like from inside, so I will use this one. Only I cannot place it inside the AMS, but I will just use the external spool holder. I got these boxes for free, but there is no additional payment from Inslogic, so this is not a sponsored video by them. But this video is still sponsored, actually the whole channel, by Polymaker, who is supporting my research activity. For some overall thoughts, and later we check the website for some additional informations, these technical filaments should be very tough. Except the PC, I'm not sure here, because I tested polycarbonate filaments which are very brittle and very tough, depending on the additives. But every PC ABS filament I tested so far is extremely tough material, and sometimes it didn't even broke under half kilogram hammer on my DIY impact tester. About ABS, it is much tougher compared to the PLA or PETG, but this one is reinforced with glass fibers. 10 is probably the percentage of the fibers in the filament, and this will make the material more brittle. But why I like these fibers in the ABS or ASA is that they will reduce the shrinking. This means easier printing and better dimensional accuracy. But how does it affect the other properties? Well, we will see in this video. And another important property of these three filament types compared to the PLA or PETG, they have much higher temperature resistance, which will be also tested in this video. Let's see a few specifications from the website.
Let's start with PC, heat resistant up to 101 degrees Celsius, excellent mechanical properties and high impact strength, so this is one of those tougher polycarbonates. PC ABS key features: high durability prototypes, functional mechanical parts, pre-dried, but interesting they don't mention that this is a tough material. ABS-GF10, I really like these specifications: ultra high strength, stronger than regular ABS, heat resistant up to 104 degrees Celsius, surprising, low warping and excellent dimensional stability, which is not surprising thanks to the glass fibers, and it is pre-dried. The prices approximately, they are different for the Europe or USA, and I calculated the dollars, so PC is $49, PC ABS $54, and the glass fiber ABS is the cheapest, $37.
Interesting, the print temperature range on all three filaments is equal between 260 and 280 degrees Celsius. For these two it's okay, but usually for the no fiber reinforced ABS it is lower. Probably here it can be higher because the glass fiber will increase the printability and overhangs should come out nice even with this high temperature, and bigger temperature will still give us better layer adhesion. And nice to see that they include here the information about the empty spool weight, which is 232 grams. But I'm still missing some drying informations. Let's start with the unboxing. ABS-GF10. Nice vacuum packaging in this better material, but the bag is not resealable. I think we can even reuse this spool for the refill kits. Maximum temperature of the spool is 110 degrees Celsius for the drying, but of course for the ABS we have to dry it on a lower temperature, and looks like this is the natural color for the ABS. Let's see how brittle is it. Okay, let's measure it. Start angle 25 degrees. Around 85, but I'll check the footage, so moderately brittle, it's fine. Polycarbonate, similar packaging, also on the spool with maximal temperature resistance of 110 degrees Celsius. Natural color of the polycarbonate, almost looks like white, but we will see it printed. End of the filament was glued. Okay, this is not brittle filament, no need to measure it. PC ABS, I'm curious about this smaller spool. Similar vacuum packaging. This is a refill kit. Uh-oh, I have a problem then. Okay, let's see the other spool. Unfortunately, currently I don't have even one empty spool for this, so I have to use the bigger one. Interesting, the temperature resistance of this spool is only 90 degrees Celsius, so lower than the previous two. Maybe it is not so sensitive to moisture. Anyway, we don't want to dry this above 90 degrees Celsius. Let's see how brittle is this filament. Not brittle at all, no need for the measuring.
I'm starting with polycarbonate. Start profiling a slicer generic PC. Let's see the settings. 60 chamber temperature, 110 on the bed, 280 the print temperature. The maximal flow is 16 cubic millimeters per second. It is close to that 190 millimeters per second maximal speed. And the part calling, well, 6 is the max, but I need it for those overhangs. Printing is great so far. Engineering plate with the glue on it. It will be completely fine. This is the last object. And now PC ABS. PC ABS slicer setting, again start profile generic PC. 6 is the chamber temperature, 280 on the nozzle, 16 the maximal flow, but the part calling I will reduce a little bit between 0 and 50%. No warping, using the same settings like with the previous polycarbonate. And very minimally, but I can feel that smell of the ABS. And soon this printing will be finished too, no problems at all. There is no generic profile, so I'm modifying the Bambolab ABS-GF, 60 chamber temperature, 280 on the nozzle. The flow is 12, but I'm reducing this to 10. And let's see the part calling between 10 and 30%. ABS-GF, this should be easiest for the printing, but I'm printing from external spool holder. Oh, but it looks like I have to stop the printing because this filament is not dried. I'm not sure if it is visible on the screen too, but pay attention to these side surfaces. Unfortunately, this needs a drying, and then I will reprint these test objects. On the website they mention heat resistant up to 104 degrees Celsius, but drying is on 110 for hours. I'm sure this is an error. Yes, the spool is designed for this, but the filament not. Drying will be on 70 degrees Celsius, 6 hours. Glass fiber version, so it should be okay. Now it looks like a dry filament with the very minimal oozing. Definitely looks much better now. I will show you later side by side two objects before and after drying. Finished overnight. Side by side before and after drying, and I saw this so many times with fiber reinforced filaments, and sometimes it is hard to believe that this is the same filament. But in this case the drying was easy. I'm preparing a fatigue testing machine, and this filament will be included too, in a separate video. A clamp hook, also for the material comparison testing in a separate video. Something like this. I want to print few more test objects for the bending test, to test it with my new Tensile testing machine. And this ABS-GF was here on open air 1 week, and it already absorbed some moisture. I have the same test objects like before the drying. Same test objects from polycarbonate even after 1 week are completely fine. I can already see that PC ABS will be fine too. Back to the ABS-GF. Printing now on X1 carbon still without drying, because I want to check if it absorbed moisture so quickly, then maybe the drying is also very easy and one inline dryer should be enough. But on X1 carbon, the printing looks okay even without drying. Edge to the left nozzle, and again looks like undried filament, but on X1 carbon it was quite acceptable. I'm not sure what's going on here. Very ugly surface, but at least we know that the textured PI sheet works great even without glue. Again drying the spool on 70 degrees Celsius, only 4 hours.
Printing on H2D, and looks like just a minimal drying results the completely perfect printing. But why is it so much better on X1 carbon before the drying? By the way, the smell is extremely minimal, maybe even smaller than with the PC ABS. It was printed exactly in this order: H2S, X on carbon, H2D, and after the drying again on H2D. Let's see the side surfaces. I hope it's visible on the screen too. Extremely rough side surfaces on H2S and H2D. On X on carbon it is quite acceptable, and of course after the drying on H2D is great too. This means H2 printers are more sensitive to moisture in the filament, and I have a theory for this. Here we can see two hot ends. This one is for H2 printers and this one for X1 carbon. And pay attention to this hot zone, it's much longer here for the H2 printer, and this means those micro water drops will boil inside this hot zone, and here it will push out more filament. And this is only my theory, let me know what you think about it and what can we start with this information. Just quickly to measure the mass of the objects, this is H2S. After measuring the weight, I can see that these two are lighter a little bit, which is normal for this kind of porous filament. And interesting, on X1 carbon before drying and H2D after drying, the weight is very similar. So definitely X1 carbon handles better this filament with the moisture. Let's check the shrinking. I can feel some elephant foot and I will measure above it. The design length is 80 mm. Polycarbonate 79.58, which is very similar to the average ABS shrinking. PC ABS, the shrinking is bigger, that's why some companies recommended high chamber temperatures. And this should be the most accurate. 79.81, so there is some shrinking, but much smaller than without fibers. Creep test the deformation under constant load. ABS, polycarbonate and PC ABS. Locking the position for more accurate measuring. 14.12, 16.86, 16.78. Now let's jump in the time. Day 5, the last measuring. 14.22, almost no changes at all. 17.67, 17.76. Let's remove the load. I can see some permanent deformation on two objects on the right side, but very minimal. On this graph we can see the distance between the reference surfaces, and we can see more deformation on PC and PC ABS, very minimal deformation on ABS-GF. But the creeping is the difference between 2 days, and that's presented on the second graph. And we can see very similar creeping of the PC and PC ABS, and extremely minimal on ABS-GF. Basically, it stopped with deformation after day 2. Temperature test in the oven. I want to record the temperature of the first noticeable deformation. And the order is more or less what I expected. Only very pleasant surprise from this ABS-GF. It started with deformation at approximately 104 degrees Celsius. And I take them out earlier because I had some nylon in the test too. Actually not really what I expected, because the polycarbonate should have this temperature resistance and blend with ABS should make it lower. But this is what I measured, and we have a very pleasant surprise from the ABS-GF, which started with a deformation above the boiling temperature. Tensile test with horizontal printed objects. This was ABS-GF, PC, and PC ABS. Very good values for the ABS-GF and polycarbonate, and actually very similar numbers to the PLA, which is quite strong material. PC ABS, a little bit weaker for my taste, but not much weaker compared to the average no fiber reinforced ABS. Layer adhesion vertical objects. ABS, polycarbonate,
PC ABS. According to my rating for this size of the test object, PC ABS acceptable layer adhesion, ABS-GF good, and polycarbonate great layer adhesion. Shear test side-by-side horizontal printed objects. Shear test, these are printed in vertical position. Printed in horizontal position, fibers always helps here, and of course ABS-GF is the strongest, but not much weaker is the polycarbonate, and a little bit lower the PC ABS. Printed in vertical position, layer adhesion is very important, and no surprises here, the PC is the strongest. Torsion test horizontally printed, load at 90 degree rotation,
1.4, 1.5, 1.3,
and the maximum load.
1.4,
Vertically printed,
1.1,
the maximum load.
1.5.
Printed in horizontal position, the load at 90 degree rotation. The strongest is the polycarbonate, but the difference is not big. I mean, the accuracy of my measuring is 0.1 Newton meters. Printed in vertical position, this is the brake load. I thought the polycarbonate will be the strongest because of the best layer adhesion. ABS-GF is the strongest. Yes, the difference is there, not significant, but noticeable. 3-point bending test. Distance between supports is 50 mm, side by side all three materials, and I'm recording the deformation after 1, 30 and 60 seconds. And currently you can see the deformation under 10 kilograms. For me this is very important test, and very minimal deformation we can see on the ABS-GF. PC and PC ABS are very similar. Only under 10 kilograms we can see more additional deformation under this 1 minute on the PC ABS. 3-point bending test. Distance between supports is 64 mm based on ISO 178. Starting with ABS-GF, real-time speed, because it breaks very suddenly. This is polycarbonate speeded up 8 times. No break. And here you can see the graph and also the bending strength and elastic modulus. And very similar behavior with the PC ABS. No complete break. And here you can see the maximum load, bending strength and elastic modulus, but also the graph of the brake. Similar values from two measurings. These are measured numbers, this is the average from two. They're very close to each other, so in the future I will have only one test object in this experiment. The maximum load ratio is equal to the bending strength because it don't depend from the deformation, and that's presented on this graph, and the strongest is the ABS-GF. Elastic modulus, of course you saw on the footage that the ABS-GF is the strongest here. PC and PC ABS are very similar, and soon I will explain these two expressions in a separate video, because I will use them a lot in my future videos. Isod impact test, ABS-GF. Polycarbonate. Very tough. PC ABS. Similar. End results, ABS-GF, polycarbonate, PC ABS. Moving to the Sharpie hammer, ABS-GF.
PC, will it break?
PC ABS.
I was ready to move to the stronger hammer, but this was just enough.
And the results, ABS-GF, PC, PC ABS. These are two different types of the tests, but the ratio is very similar, so PC and PC ABS are very tough materials. ABS-GF looks brittle, but this is still tougher compared to the average PLA or PETG. Our results one more time: creep test, tensile test and a layer adhesion, shear test horizontal and vertical, bending test, deformation after 30 seconds, bending test, deformation after 1, 30 and 60 seconds under these loads, torsion test, horizontal and vertical, temperature test, impact test, Isod and Sharpie, and this is that new bending test based on ISO 178, bending strength and elastic modulus.
Quick conclusions.
PC and PC ABS, very tough materials. Between these two, the polycarbonate is a little bit stronger in most of the tests. Interesting, in the temperature test, a blend with ABS is more heat resistant compared to the raw polycarbonate. I'm not sure why. About the ABS-GF, very stiff material, even the temperature resistance is great. Only that a mystery with that drying. I know that most of you watch the videos with the skipping, jumping, and maybe you missed that part. Then go back and check that very interesting mystery with the moisture. This is why I'm still keeping my X1 carbon. Imagine, in most cases it is more ready to use compared to the H2 printers because it is less sensitive to moisture. Interesting conclusions. What's your opinion about that? Anyway, thank you for watching this very long video until the end, and thanks to all my Patreon supporters. Happy printing!